it's my pleasure to introduce John Hopcroft, who currently is the IBM Professor of Engineering and Applied Mathematics and Computer Science at Cornell University. John Hopcroft was born in Seattle, Washington, in the USA. He received his PhD from Stanford University in 1964, after which he worked in Princeton University as an assistant professor, after which he moved to Cornell University. In 1986, together with Robert Tarjan, he received the Turing Award of the Association for Computing Machinery for fundamental achievements in the design and analysis of algorithms and data structures. Besides the Turing Award, he has received also a number of other recognitions. And in addition to his research work, he is well known for his books on algorithms and formal languages, regarded as classic texts in the field. So he is going to tell us about new directions in computer science research.
It's a great pleasure for me. It's a great pleasure for me to be here today and have this opportunity to give you a talk about the future of computer science. I've been here for a week. I've been working with some of your faculty, talking about what ought to be taught in computer science. And I'm actually very, very pleased with the week because I think that you have some excellent faculty who are going to create some really great courses. And one of the things as I talk, I'm going to sit down because I have a collapsed ankle. I don't have as good balance, and it's just easier for me. So I hope that's okay. One of the things that I'd like you to leave with is understanding that computer science is undergoing a fundamental change. And those individuals, institutions, and nations who recognize this change and position themselves for the future will benefit enormously. And I'll just tell you a brief story about my career to illustrate this point. I graduated from Stanford in 1964 in an electrical engineering department. There were no computer science departments. And when I was hired at Princeton, it was an electrical engineering department. But fortunate for me, Ed McCluskey, who was there, asked me if I would teach a computer science course. And I had to ask, well, what do you teach in such a course? Because there were no books. There were no such courses. And he gave me 4 papers and said, if you cover the material in these papers, it'll be a good course. What I didn't realize at the time was teaching that course made me one of the world's first computer scientists. And that meant when our government was looking for a senior computer scientist, I was probably on the short list. So when I was in my 40s, I got a call from our White House telling me that our president wanted to appoint me to the National Science Board, which oversees science funding in the US. Now imagine if I had been in high-energy particle physics. I would still be waiting today for the senior faculty ahead of me to retire to have that kind of opportunity. Okay, when I tell this story to my students, they say, well, you were just fortunate because you started your career in 1964. But something that I'm going to tell the students who are here today, you're also fortunate because there's a fundamental change taking place, and computer science is shifting from being focused on making computers useful to what they're actually used for. And so I'm going to talk a little bit about that. I'll give you some examples of the mathematics that students are going to need for the information age, and then some applications where the mathematics will be used. And I'm going to start with high-dimensional data. Now, one of the things about my intuition, it was formed in 2 and 3 dimensions. And it turns out that high dimensions are fundamentally different than low dimensions. If you randomly generate points in high dimensions, you'll find that the distance between any pair of points is the same. And this says if you're going to do something like clustering, it's likely to be very unstable. Another thing that's different is if you take a unit radius sphere in high dimensions and calculate its volume is going to be essentially 0. And in fact, in the limit, as the dimension goes to infinity, the volume of the sphere goes to 0. And let me just show you how you can see why that's true. Let me just generate some points from using a zero mean unit variant Gaussian. So I'm going to generate a vector x where each coordinate x is a Gaussian variable of zero mean and unit variance. And let's say I want to know what the distance, the square of the distance from the origin of this vector x, or the square of the length of the vector x. And I'm going to calculate the expected length. So what I do is I take each coordinate, I square it, and add them up. And I take the expected value. And I then interchange the order of the summation and the expected value. And this is something that you should know, is that the expected value of the sum is the sum of the expected value. So I want to compute the expected value of the square of each coordinate. And since each coordinate was a Gaussian variable of zero mean, the variance of that coordinate is the expected value. And so the expected value of each coordinate is 1, and they're d coordinates, so I add them up. The expected squared length is d, or the length of the vector is square root d. It'll be tightly concentrated about that value. So let me generate a number of random points in high dimension. It'll turn out that all of these points will lie on a narrow annulus of radius square root d. Now what I'm going to do is I'm going to put a sphere centered at the origin, a unit radius sphere. And what would happen if I integrated the probability distribution over that sphere? Well, since there are no points in the sphere, the answer is going to be 0. And the question is, how did that happen? So I'm going to integrate the probability distribution of a zero mean unit variant Gaussian over a unit radius sphere centered at the origin. And I'm going to get the answer 0, because there's no points generated within there. So the probability, the integral of the probability must be 0. But since the probability density is maximum at the origin, and that's where it's the highest value, the only way that that integral can be 0 is if the volume is 0. And indeed, if you calculate the volume of a unit radius sphere, you'll find out that it's essentially 0. And this is something that is quite different if you take a three-dimensional sphere, unit radius sphere, and it has volume, and you've probably calculated that. But let me also look at the distance between two randomly generated points. So I'm going to generate a vector x and a vector y. I'm going to take the difference, square it, and find the expected value. And I multiplied out x minus y squared. That's these three terms. I multiplied out the coordinate x sub I minus y sub I squared. And when I take the expected value, once again, I'm going to move the expected value inside the summation. But you'll notice that this middle term, this 2xi, yi, disappears. Because the 2 points that I generated are statistically independent. There's no relationship between x and y, and therefore their coordinates are independent. And therefore the expected value of x sub I times y sub I is equal to the expected value of x sub I times the expected value of y sub I. And if the expected value of x sub I is 0, that term disappeared. And so you see that the distance between these squared is 2d. Now, the reason that's interesting is if I look at 2 points that I generate. So when I generate x, let me change my coordinate system so that I put x up here at the North Pole. And then I'm going to generate y, and it'll lie out here. Each of these points is approximately square root d from the origin, and the distance between them is square root 2d. That means if you generate 2 points, 2 vectors uniformly at random, they're going to be essentially orthogonal. Now what's interesting about that is this point is lying on the equator. It has to lie on the equator if I put the first point up at the North Pole and the second point is orthogonal to the first. But if it lies on the equator, that says all of the surface area of a sphere in high dimensions is at the equator. Okay? That's fundamentally different than 3 dimensions. If you fly to Asia, you're going to spend a lot of time flying over the Arctic. There's a lot of surface area in a 3-dimensional sphere. But in a high-dimensional sphere, there is no surface area near the North Pole. It's all at the equator. Now that may bother you a little bit, because you could pick the North Pole any place you want. Pick a random point on the sphere, and there'll be no surface area around it. But it will determine an equator, and all of the surface area of the sphere will be at the equator. Okay, I just point this out because it's just important to understand high dimensions and that it's fundamentally different than low dimensions. So I'm going to move on to a number of topics which are kind of interesting that you'll probably be dealing with. One of them is social networks. In the past, sociologists could only work with small groups of people, say 1,000 or so. But today, you have the ability to work with tens of millions or even hundreds of millions. You can take Facebook and you can explore how individuals interact on Facebook. And one important activity in social networks is studying communities and how communities form, how they evolve. If you have a community of friends and it starts to grow, if you have 10, 20, 50 friends, you may have a community that's coherent. But when you get 1,000 friends, something's going to happen to that community. And the question is, does it bifurcate into multiple communities, or just what happens? Okay. So let's look at communities for a little while. This community in blue is what I call theoretical computer science. And I put myself in it. Now, at first, researchers thought a community was a set of individuals. And there's an edge between 2 individuals if they interact with one another. And it's a group of individuals who have more interactions within the community than outside. But that's not true because an individual is in many communities. And notice that even if the probability that I would connect with someone in theoretical computer science was much higher than the probability I would connect with someone outside, the fact that there's only a few thousand theoretical computer scientists, but there's 1 billion people outside, says I'm likely to have far more connections outside a community than inside a community. So one of the definitions is to just define what we mean by a community. And are there different types of communities? And I'll give you some evidence to suggest that yes, there are communities and different social networks are fundamentally different, and we're not going to have one definition of community which is going to survive for all applications. It's interesting to see how communities evolve over time, and I'm going to focus a little on this bottom issue. Are all social networks similar, or do we need different algorithms for different types of networks? If you look at the current literature at people who have community finding algorithms, they seem to believe that all networks are the same, and that if you have a good algorithm, it'll be good for all networks. But first of all, let me just focus on the word similar. What do I mean when I say two social networks are similar? When I was an undergraduate, graphs had only 15 vertices or so. And when we said two graphs were similar, we said they were almost isomorphic. But that's not the definition that's going to work today, because let me put up two graphs that I think are similar. These are two randomly generated GNP graphs. And in some sense, I believe they're similar. But if you try to find an isomorphism from one to the other, you're not going to have anything close to that. But I would also like to say these two graphs are similar. They're structurally similar, only one's twice as dense as the other. And also, I would like to say these graphs are similar. It's just one is twice as large. Now, the reason I want to call them similar, even if they're a different size, if you consider Facebook 15 years ago, and you consider Facebook today, it's grown immensely. But I don't believe the structure of the graph is growing. It's just changed in size. And so an interesting mathematical issue is how do we define similar in this new world? So GNP is a model of a random graph. And the model works as follows. If you want a graph with n vertices, you put down the n vertices, and then for each pair of vertices, you flip a coin, which will come down heads with probability p. If it comes down heads, you put the edge in, otherwise you don't. And the graphs that I generated on the previous slide were GNP graphs. Two graphs are similar. I'm claiming they're similar, even though they have only 50% of their edges in common. And so this is an important issue to figure out how to make this definition. But even though I don't have a definition of similar, I'm going to convince you that different social networks are not similar. And the way we did this is we selected 8 social networks. DPLP is a database of research papers. Amazon will have a graph where the vertices correspond to products. And there's an edge between two products if they're bought at the same time. We took some Facebook networks and we took some biological networks. In the biological networks, the vertices correspond to the genes, and there's an edge between two genes if they interact. So we selected 10 community detection algorithms, and we applied each community detection algorithm to each of the networks, and we created a number of communities, about 100 communities by each algorithm and each network. And we partitioned the data into a training set and a test set. So for each network and each detection algorithm, we took 50 communities. And what we did is we determined the number of features of communities, so we could represent a community by a vector of features. And then we trained the support vector machine to recognize which network each of these communities came from and which algorithm had produced it. Afterwards, we took the test set and applied it to the support vector machine. And the support vector machine was able to correctly identify in most cases, which network a community came from and which algorithm produced it. And what that suggests is there must have been something different in each network that the support vector machine could learn, and something different about the communities that these algorithms found that the support vector machine could learn. And so we concluded that, well, this is strong evidence that the networks are different. And also the community detection algorithms find different types of communities in a network. And this suggests the kinds of research that people are now doing. And I should mention one thing about my talk. I'm just selecting a few items, that there are just thousands of open problems that are mathematical and they're interesting, that people are working on, and that it's important that students be exposed to them so that they will become interested in them and have the techniques to work with them. So I'm going to talk a little bit about structure in a network. Suppose I were to classify papers, journal articles. Say I went to the physics archive and I clustered it. I might get physics papers, chemistry papers, math papers, and biology papers. So in my networks, the vertices correspond to research papers. And there's an edge between two papers if they are similar in content. And I guess I should mention, how do I determine if two papers are similar in content? What we do is we sort the words that occur in the paper, and we form a vector where each coordinate corresponds to a word in the English language, and we put the number of copies of that word that occur in the document. And this is called the word vector model. And so we represent a document by throwing away all of the information about the order in which the words occur in the document. But it turns out this is how search engines work, and this is how people who deal with documents work. But if you were to cluster this network, this might not be the only way to cluster it. This is clearly the dominant structure, but there may be a hidden structure. Survey papers, expository papers, and research papers may use different vocabulary, slightly different. And so you ought to be able to cluster them this way. Or you ought to be able to cluster whether the paper was written by an English-speaking author, an Asian author, or someone else. And I'll just mention, I teach in countries other than the US. I teach in China. And when I was in China, I was teaching a course on how to do research. And so I gave each student a research problem. And one of them was to determine whether Caucasian authors published less than Asian authors. And in particular, did Asian authors who were in the United States publish less than Asian authors in Asia? And what they did is they wrote some code. They found a database that had 50,000 names, and each name said what nation the person was in. They trained a support vector machine to classify these names. When given a name, say what country the person was from. They then took the support vector machine and went through all the conferences they could find, stripped the authors out of publications, determined from the author's name whether they were Asian or Caucasian. And in the end, what they found out is that Asian authors do indeed publish almost twice as many articles per year as Caucasians. But if it's an Asian author in the US, their publication rate is somewhere between Caucasians in the US and Asians in Asia. It's just to give you an idea of how you can extract information from the tremendous amount of large data that's out there. And believe me, companies in the world are using the information they have to extract enormous amounts of information. Other things you might discover is you might want to classify papers whether they were established authors or young authors. There may be a slight difference in the words they use and the distribution of words. To give you another example, suppose I ask you to cluster these letters. Clearly the dominant classification, you would put the A's together, the B's together, and the C's together. But this would be the dominant classification, the dominant structure. But you might notice that some of the letters are slightly different color than the others. Some of them are black and some of them are dark gray. And you might classify them by color. Or you might notice, if you really looked at them carefully, that there are 3 different fonts. Okay? So when you're in a social network, there's a dominant structure. And it's not clear to me that you want to spend a lot of time finding the dominant structure, because it's probably easier to find a catalog somewhere that will give you that kind of information. But what you might really want to find is hidden structure. Suppose there was a bunch of terrorists who were using Facebook to communicate. They would not be very dominant, but they might be like this type font, and you might like to be able to find them. So let me show you just a little bit about the structure of graphs. Here, what I'm doing is I'm creating an adjacency matrix for a graph. The rows here correspond to vertices, the columns correspond to vertices, and I'll put a 1 in here if the 2 vertices are in the same cluster, they communicate, and I'll put a 0 if they don't. So what I did is I formed a bunch of small communities, and I put a lot of edges inside these communities, and no edges outside yet. Okay. Then the next thing I did is I added some random noise. So I just randomly put a bunch of edges in, connecting people in different communities, but not as many edges as within communities. Then what I did is I randomly permuted the vertices to give you this matrix over here. And when you have a social network, you have an adjacency matrix like this. And what you're asked to do is find the permutation of the vertices, which will convert the matrix back to the dominant structure. So I guess this here. Okay. Now, one of the things that we noticed, and everybody noticed, that people who create clustering algorithms, when they tested on synthetic data like this, the algorithms worked very well. But when they tried the algorithms on real data, they didn't work quite as well. And one of the research questions is why? And it turns out the reason why is this noise here that I put in is statistically independent. But in real networks, you have a different structure. So let me create another synthetic graph, but slightly differently. Again, I create my adjacency matrix. And I put some communities in. But instead of adding random noise, I permuted the rows and columns to get this matrix. Oops, let me go back. And then I put another set of communities superimposed here, and then permuted the rows again. And what you have in a social network is an adjacency graph like this, where there are 2 or more different types of structure in the graph. And when you find the structure, the question is, which structure do you want? Do you want the dominant one? Or do you want a weaker hidden one? Okay. So here is an adjacency matrix, which I created, and I gave it to some students, and I said, find the structure. Well, very quickly, some students came back and said, we found it. They found 3 communities with a large number of edges within the community and 0 edges between communities. And so the question is, what kind of a grade should I give them? Well, a little later, a few other students came in and said, we found the structure. And they had found 5 communities. Again, the communities have a fair number of edges in them and no edges between them. Well, which one is right? It turns out they're both right because I embedded both of these structures in this graph together. Okay? And so this just gives you some idea of what you're dealing with when you're looking at the structure of social networks. I will return to social networks a little later, but I wanted to talk about another technique, Markov chain Monte Carlo techniques. These come up in many applications. One application would be a doctor's office. The doctor has the following problem. He knows that there are various diseases, and so he puts a vertex here for each disease that he's aware of. There are a number of causes, like what food did someone eat, what country did they visit, and various other things. And there are symptoms. And the problem with the doctor, when you walk into the doctor's office, is he talks to you and he figures out what the probability of these causes are, and he determines your symptoms, and he wants to find out which disease is most probable. Now, what these arrows represent is this cause has a certain probability of creating this disease, this cause has a certain probability of creating these two diseases. So from this graph, he may have 100 variables here, let's say. He's going to have a probability distribution with 100 variables, and he's going to want to do various things, like find out the most probable disease and things of that type. And this is just one instance of a large number of problems like this. So let me just look at one of them. You quite often have a function with, say, 100 variables and a probability distribution. And maybe I want to just calculate the expected value of this function. So what I would do is I would take the function times the probability, and I would sum over all the possible probabilities. Now, if each xi has 10 values, then there's 10 to the 100 terms. Okay, and just to give you an idea how large that is, the number of atoms in the visible universe is estimated to be 10 to the 70th. So this is an enormous sum, and I obviously can't do it on a computer. So the solution is, let's sample. Let's randomly sample 100 terms and calculate this sum, and then multiply it by some fraction of the size of my sample to the total size. Okay? But I can't sample uniformly at random, because it is probably the case that this probability function is 0 for almost all of the samples. So somehow I've got to sample with probability proportional to the value of the probability function. And the question is, how do we do that? Well, what we do is we use this Markov chain Monte Carlo technique. We're going to construct a graph whose stationary probability is this probability function. The stationary probability is if you do a random walk in a graph and you calculate the frequency at which you visit the various vertices, that frequency will converge to a stationary probability. I guess one of the things I should just point out, though, that if you push out the probability and ask, does the probability distribution converge to the stationary probability, it might not. I mean, these are things students should be aware of. But anyway, I'm going to do a random walk, and I'm going to select a sample after some number of steps. But how many steps should I take? I've got to take enough steps that my walk converges to the stationary probability. You're probably a little bit nervous now. This graph has 10 to the 100 vertices. How am I going to store the graph in the computer? Obviously I can't. Well, you don't need to store the graph. All you need is an algorithm that tells you, if you're at a given vertex, what the adjacent vertices are. And that's the only information I need to do a random walk. I go to an adjacent vertex, I apply the algorithm to find out who's adjacent to that vertex, go to an adjacent vertex, and do my random walk. So storing the graph is no problem. I'm not going to do it. But how long a random walk is required? If there are 10 to the 100 vertices, and I have to walk in time proportional to the number of vertices, I'm never going to reach the stationary probability. It turns out that if we create an expander, if our graph is an expander, and this is an important thing for students to understand what an expander is, the walk will converge to the stationary probability in a number of steps which is logarithmic in the number of vertices. So instead of taking 10 to the 100 steps, I only have to take some constant times 100, say maybe 10,000 steps. I then select a value for the vector x. I then walk another 10,000 steps. And the reason I have to walk another 10,000 is I want my second sample to be statistically independent of the first. Okay. And I'm going to select 1,000 samples. I'm going to calculate that sum, and I'm going to estimate the probability. And I will get an answer which is very close to the correct answer. I'm going to bring up another topic, and that is topic modeling. This comes up in many areas. You may wonder how, if you ever bought an item from Amazon, they sent you back an ad, and the ad was probably about something that you were interested in. How could they figure out what your interests were based on a single purchase? Well, the reason is a method that I'm going to show you is in this area of topic modeling. There's some mathematics which will tell you how to answer that. I'm going to actually talk about topic modeling with respect to documents. Whoops. So I have documents here. Each column is a word vector model representing one document. The rows here are the words. And an entry here is for this document, how frequently this word appears. Now, one of the things I would like to do is I'd like to simplify this matrix. If I have hundreds of thousands of documents and thousands or tens of thousands of words, it's a big matrix. So what I'd like to do is I'd like to factor it into two smaller matrices, one of topics and the other of documents. And basically, a document is made up of a number of topics, and each topic has a probability distribution of words. Okay. Now, if I want to do this factoring, you might say, well, just do a singular value decomposition. And by the way, singular value decomposition is very important for students. Not only because you can factor, you can find a good approximation to a matrix, but it turns out that PageRank, which is the first singular vector of the web graph, happens to be, you would get it from singular value decomposition. And it's also important to know how to calculate the first singular vector of a matrix, which is 20 billion by 20 billion. But the first thing is that matrix is a sparse matrix. There are 20 billion web pages. Search engines have found about 20 billion web pages. But the World Wide Web is not a strongly connected graph. It's very sparsely connected. Some web pages probably don't have any links to other web pages. But how do you find the first singular vector of a matrix, which is 20 by 20? And how do you do it in a few seconds? And how do you do it on your laptop? These are things that I understand some of your faculty are going to be developing lectures on and are going to be in courses for you. But it turns out that using the singular value decomposition is not going to be a good way to factor. The first singular vector has all positive entries because it's a probability vector. But the second singular vector has got to be perpendicular to the first, and that means it's got to have negative entries. And if I use the singular value decomposition to factor, I'm going to have negative entries in here. And I'm going to have topics in which some word appears a negative number of times. I don't want to do that. I want to have a non-negative matrix factorization. Okay. So, in general, non-negative matrix factorization is NP hard. However, in special cases, there are polynomial time algorithms for doing it. And one of them is if there are anchor words. And an anchor word, in our case, is a topic. An anchor word for a topic is a word whose row in the matrix is all zeros except in one column. So it's a word like baseball. It is only going to occur in the topic of sports. It's not going to essentially occur in economics or education or other topics. And by the way, when I need a topic model, I don't need a perfect topic model. I don't need all zeros. All I need is that the vector is close to zero except for one large entry. Okay, so let me show you how to do non-negative matrix factorization. So I have this matrix A, and I want to factor it into B and C. Now, there are many factorizations, but if some row of C was a positive linear combination of other rows, I would delete it, and I would come over here to the columns of B and correct it, so that when I multiplied B times C, I would still get A. So I'm going to assume that no row of C is a positive linear combination of any other row. Okay. Now, if there is an anchor word for each topic, that says some multiple of each row of C is going to appear in A. And if I can find them, then I would have C, and what I could do, I could then solve for B. So what I'm going to do is I'm going to come over here in A, and I'm going to eliminate rows of A, which are positive linear combination of other rows. When I do that, I'll have C, and I'll have my non-negative matrix factorization. I'm just going through a number of these things, which I've only selected a few topics, but to give you the range of math that's important for students to know. And I'll just tell you that in a U.S. university, by the time an undergraduate graduates, he could almost give you this lecture. He or she would understand all of these topics. Even though there are a large number of them, it turns out they're related. And so as you start to learn them, it's very easy to see a new one. It's not learning something from scratch. Okay. I'm going to move on to another topic called deep learning. This topic has become of interest in the last few years for the following reason. There have been a number of contests in doing image recognition or speech recognition. And the winners have all of a sudden started to turn out to be people who used deep networks. Networks where there's input data, then there's a row of threshold logic, another row of threshold logic, and usually there's about 7 or 8 levels. And then some output. The output's a little different in that case. They use something called softmax to calculate probabilities. But I just wanted to put up one picture of a network to give you some idea of what it is. Well, when these networks started to becoming the winners, Google and Microsoft started to use them in a different way. See, the people in image recognition were using them in supervised learning. But Google and Microsoft have an unsupervised learning problem they want to solve. They have 100 million photographs, and they would like you to be able to put in a request saying, give me a photo of a cat sitting on a beach watching the sunset. And they want, within a few milliseconds, to give you the photo. Now, if you could do supervised learning, it would be fine. They could hire some people to label 10,000 of these photos, except for the fact that how do you label a photo? You're going to have to put hundreds of labels on every photo. If it's a woods, if it's a house in the woods, you're going to have to say a house, it's color, there's trees, there's plants around it, there's all kinds of things. The photo was taken in the evening. This just doesn't seem practical. So they would like to have a network, which they don't have to train in some sense, that would simply learn what photos were about. And when you asked for something, they would give it to you. Okay? And by the way, furthermore, they want to put this on your iPhone. And some things I haven't talked about, but in the lecture I'm going to give tomorrow, I'll talk about putting census data on your iPhone and some things like that. But what they did is the following experiment. They trained a network. They put a photo in here. They put 7 levels of hidden gates, and then trained it to reproduce the photo out here. So let me give you some idea of the dimensions involved here. To get a photo, it's an array. Let's just say it was just 1,000 by 1,000. They take each row of the array and can put them together to form a vector, which is a dimension 1,000,000. So this inputs here, there's 1,000,000 pixels. In here, they have only 10,000 gates. And you might ask the question, oh, and they put in maybe 100 million photos. And you might ask, with only 10,000 gates here, when that's much smaller than the 1,000,000 pixels here, how can they possibly represent all these 100 million photos? Well, the answer is, if each of these outputs could just be 0 or 1, and there are 10,000 gates, there are 2 to the 10,000 codes, and so there's plenty of codes to encode anything you could possibly stick into this network. But this coding here is maybe a better encoding of the photo than the initial photo. And as you go through this network, each level, as you go along, you get a better encoding. And then they looked to see what some of these encodings were, and lo and behold, they found one of them was pictures of cats. Even though they had never done any training, labeled any photo having a cat. All of a sudden, they got excited and realized that this might be a way to solve their problem. One of the things I'll mention, you've got to realize how many inputs there are here. If there are 10,000 gates here and 10,000 gates here, each gate here has 10,000 weights. And the way they trained this network was by stochastic gradient descent. And 10,000 times 10,000 is what, 100 million times, say, 10 levels is 1 billion gates. How the devil did they use stochastic gradient descent? There's another problem that this network, the loss function, had better be differentiable, so they had to make some modification for that. And it turns out you couldn't possibly use stochastic gradient descent the straightforward way, because these weights back here would take centuries before they converged to anything. I'll show you how they did it in just a second. But to give you an idea of the scope of this problem, they had 10,000 computers, and they ran for 2 to 3 weeks. Okay. So when we're starting to do research with this with students, we obviously are scaling the problem down a little. But the way they did this network is they trained it 1 level at a time. So what they did is they took the inputs, the first level of hidden gates, and they trained these weights to produce the output. Once they did that, they went back here, they froze these weights. They then trained these weights to produce the output. Then they froze these weights, they added the next section, the next section, the next section. So they only had to train one section at a time. Okay. There's also a lot of other differences. You don't want to overfit, so one of the things, you put a requirement that these gates can only activate for a small number of inputs. And there are various things you could do. What you might is knock out some of these, randomly knock out some of these weights to prevent overfitting. But also, when this was used in image recognition, the first couple levels were different. Instead of having every input connected to every gate, what they did is they took a 5 by 5 square and they connected those 25 pixels to a gate. And then they moved that square over the entire pattern. So they had a bunch of gates here. They had closer to 1 million gates, but each gate had only 25 inputs. And that kind of a layer is called a convolution layer, and they used 2 convolution layers. The reason they did that is if you have a picture of a person, you may want to recognize an eye, but you don't care where that eye occurred in the photo. And by having this convolution level, they were able to remove where something appeared in the photo. Rather than that, they just said, does it appear somewhere? Okay? And this works very well for edge detection, corner detection, and things like this. But one of the things they discovered is they took a network, they trained it for a set of photos, and then they froze the weights at the first level for that set of photos, and then they retrained the network for a totally different set of photos. The first photos may have been pictures outside, the second set may have been pictures inside. But the second set trained just as well having these weights frozen. And what they concluded from that is what these first gates learned had nothing to do with the actual photos that were being shown, but had to do with photos themselves. And so the gates were useful for any collection of photos. And people are starting to learn things like this, and so this area of deep learning is a major area of research now in computer science. Some of the questions in this area is, what do individual gates learn? How does what the second level gates learn differ from what the first level learns? How does what a gate learn evolves over time? So as I'm training this network, what happens? And what if you try training with 2 different sets of starting weights? When you start gradient descent, you use some random weights to start. And if you have a different set of random weights, do the gates learn the same thing, or do they learn something different? And if you learn on 2 different sets of photographs, do the gates learn the same things? I'll just mention one interesting thing. A student was looking at what do gates learn, how does it evolve over time? And for each gate, he had an activation vector. And each coordinate of this vector corresponded to one photo. And he instead of using photos, he scaled the problem down to, was it a 10 by 10 grid, where he had pictures of rectangles. And for each rectangle that he showed, he looked at a gate and said, what was the activation? Then he had another vector, which was the area of the rectangle, and he multiplied these 2 vectors together to see whether the vector correlated, what it learned correlated with area. And what he noticed was the following phenomenon. Initially, 3 gates would start to learn area of rectangles. And then at some point, there was a switch. And one of them continued to learn, and 2 gave up and went on and switched and started to learn something else. And interesting research is, how did this happen? how did this combinatorial optimization determine that having three things learn the same feature was not important and turned two of them off to learn something else? It's an interesting question. And there are all kinds of questions like this that we don't know the answers to. So, hidden structure. So it was known that clustering algorithms worked better on synthetic data than real data. Why? And we said synthetic data has uncorrelated random noise, whereas what appears to be uncorrelated random noise is really weaker hidden structure. So what we did, we took 6 clustering algorithms from the literature and we applied them to several social networks, and we found the dominant structure. Then what we did is we randomized the dominant random structure so it was no longer there. And we applied the algorithm again to find the hidden structure. When we found the hidden structure, we went back to the original network and randomized the hidden structure and refound the dominant structure. And it turned out that this technique improved all 6 of the clustering algorithms, which were viewed to be the 6 best clustering algorithms. But the technique was also able to find as many as 7 levels of structure in some networks. So let me just show you very quickly how this works. This is on synthetic data, and we applied one of the clustering algorithms from the literature. The circles are the big circles are what the algorithm found for the dominant structure, but the color is what the real structure is. The yellow should all be together. But you'll notice it did a reasonable job. It found something, a cluster which is mostly yellow, one which is mostly green, mostly blue, light blue, mostly dark blue. Then what we did, though, is we randomized this, and we found the hidden structure. And again, the big circles are what the algorithm found, and the colors are what it was supposed to find. This case was not so good, but what we did is we then randomized this hidden structure so it would not disturb the algorithm when it was finding the dominant structure. And we reapplied it, and this is what it found for dominant structure the second time. And then when we randomized this is what it found for the hidden structure the second time. And now the hidden structure is starting to evolve. And let me show you that in a little better slides. This is looking at the dominant structure. On the left is the first thing the algorithm found. After randomizing the hidden structure, this is what we found. Notice this community here has got much better. This community has improved. This one's about the same. This got a little bit better. Roughly the same. These just disappeared apparently into one. And what happened to the hidden, or wait, the dominant, oh, this is after we repeated the dominant. This is then the second, and then this would be the next iteration. And you notice that things are getting better. And then if we go, I think, one more iteration, this is what they finally found. And they did pretty well, except for 2 communities which somehow got merged together. And when you look at the hidden structure, this is initial, this is 1 iteration. Let me go 2 iterations. And you can see at 2 iterations, you really start to get the dominant structure. This here, the green, which was scattered all over here, all of a sudden comes out. The blue gets merged together, the red. And you can see how it is eventually pulling out the dominant structure, and it finally converged. And doing this, we go back and we randomize both the dominant structure and the hidden structure, and then we find a level of structure underneath. And we do this, and in some networks, we can go through and find 7 levels of structure. Now, this was on synthetic data. You might ask the question, what if we tried some real data? So let me show you what happened on real data. We took Facebook, And someone had gone through and found all of the students at Rice University. And so we clustered it using a regular cluster algorithm. And we happened to, since we ran them through and found out what the dominant structure is, it turns out it's going to be dormitory in which the student lives. And the color here represents, if it's red, they live in one dormitory, if it's yellow, it's another dormitory, and so forth. And this is the dominant layer initially, and after we randomize it, find a hidden structure, randomize that, and go back and find the dominant, we got something like this, where we're really starting to find the dormitories people live in. If we continue and do this another time, this one, which was just a collection of all sorts of people, they get placed in the right dormitories. This is where two dormitories were merged, they get separated. And finally, this is what we pretty much have every student in the dormitory they live in. Okay? Now, you might ask, what was the hidden structure? Well, the first shot at the hidden structure was this. And what we did is, afterwards, we found out that this is the year, whether they're freshman, sophomore, junior, or senior. And so we used color for that. And you notice that the algorithm, in its first attempt, found 1, 2, 3, 4, 5, 6, 7 years. After purifying it a little, it's a little bit better. Another step, finally we're merging down to where it looks like we've got 3 years. You'll notice 2 of the years are still clustered together, but when we go another iteration, what we do is we have the students clustered, whether they're freshman, sophomore, junior, or senior, and you'll notice that there's 2 little cliques, 2 little clusters in here, and these were students who didn't finish in 5 years or 6 years. Okay, so this is the structure you can pull out of Facebook. Now, not only did we pull this structure out, but after we went back and randomized the hidden and the dominant, it turns out we actually found 4 levels of structure in Facebook, but we couldn't figure out what the other 2 layers corresponded to. It may be people who play a given sport, it may be people who like certain movies, there's no telling what. Could be their religion, could be anything. But it's pulling out that hidden structure is what you really want to find. I mean, for example, if you were trying to find a terrorist group, it would be one of these hidden levels that we don't know what they are. Okay? And in some networks, we were able to find as many as 7 levels. I stop here. I'm going to thank you for having this opportunity, but I'd like to just summarize a couple things that I'd like you to walk away with. One, you live in a time of change, and a time of change is a time to position yourself for the future. Don't do what some faculty member whose career was the last 30 years says, this is what I found great, trying to work on this. Position yourself for the future. And secondly, in computer science, there are an enormous number of interesting mathematical problems that people really want the answers to. And some of them are answers which have billions of dollars of value. And there's just such a wide range. And these problems have not been worked on by a lot of bright people for decades. So there's a chance that if you're an average person like myself, you can work on them and have fun. You can solve them. And so that's what I'd like to leave you with. I'm going to give another talk tomorrow. The talk will overlap this a little, but I picked a different set of examples. So I'll talk to you about zero-knowledge proofs, how you can prove something without giving someone any information about what you're proving, things like that. But there will be a fair amount of overlap. But thank you for this opportunity.
Is capture still safe You seem to be doing a great job at recognizing patterns. There's CAPTCHA still saying. That system for detecting if you're logging into something, if you're a machine or a human.
But you mean what you have to look at this.
Recognize the letters and
yeah, those things really annoy me because I don't think they keep machines out. They keep me out. Because quite often I can't do the same thing. I don't know what the status is of people who have tried to recognize those and determine what the characteristics are. But it would be an interesting problem because you could very quickly get yourself a large data set, and it's small enough. By the way, you can use low resolution photos. Most of the work that's done with Microsoft and Google, they use a million pixels. It's small for them. They use more like 10 million pixels and so forth. But 3,000 pixels is enough to do work in this area. So I think a caption 3,000 pixels would be enough to capture it and try it. Yeah.
You talked about 4 papers for your fifth course.
Oh.
Do you remember which ones?
One of them was on regular expressions. One of them was the Raven-Scott paper on finite automata. I'm not sure what the other two were, but they were relatively basic things of that type. And if you ever used the first version of the book that I wrote with Ullman on finite automata, that was basically the course.
If you could tell the people here how you go to the practice with this, it's very good theoretical, but if here in Mexico we want to make some development, how we can set it down to computer, what kind of framework you use, or where do you put this in practice?
So I should tell you that these problems all come from practice. For example, you get email. Some of it's spam, some is not. What you'd like to do is label a few, train a support vector machine, and have it eliminate spam from your computer. So I was just down in South America working with some faculty, and one of them had a problem. They actually were consulting for a bank, so we worked on their problem. The bank gets 1,000 transactions per day by telephone. They convert these telephone conversations to digital, and some of them are suspicious, but they don't want to spend time looking at 1,000. So they wanted to write a computer program which would determine which phone calls are suspicious, that some person ought to look at this transaction and see what's going on. So there's such a close connection between these problems and real problems that I don't really think of that, but I think it's really important for Mexico's economy that you start producing students who are really talented and understand these techniques and algorithms so that they can help organizations and companies do things. I mean, I'll just give you a few examples. In the US, when the government is going to propose some new legislation, they have to put it out for comment. And if it's on a politically sensitive area, there'll be millions of comments. What do they do with them? Do they just throw them away? Well, a computer reads them. And there is sentiment analysis, which is an area which will say whether this is positive or negative and on what part of the proposal is it positive or negative on. And then it classifies these million, and all they have to do is pick a representative from each category. So almost anything you touch today, people are converting it into the mathematics that's needed to make it possible to solve. It's because the scale of the problems are beyond what humans can do now.
Do you use Spark or Hadoop frameworks, or what kind of computer science framework? Spark, Hadoop, MapReduce, and something like that, or what kind of framework do you use?
There are different, in computer science, we have to educate the student for different things. I guess what I'm talking about now, I'll call machine learning. So we give them a couple of courses in machine learning, which would cover everything I talked about. There's another set of courses, how do people deal with large sets of data? And there's another set of courses dealing with security and privacy. And these are all separate, and I'm not really knowledgeable in these other areas of computer science. Computer science has grown to be so large that there basically are those faculty who understand systems, there are those that understand machine learning, those that understand scientific computing, those that we talk to one another, and we eat lunch together, which is very, very important that faculty know one another, even though they're not working in the same area. And by the way, computer science has spread so much, it's no longer in the computer science department. It's in economics, it's in sociology, it's in biology, it's in operations research, and what you're starting to notice is that co-authors are in different departments. But I guess you're entering the information age is all I'm telling you. Yeah.
Could anyone use this structure finding method for clustering? Because I happen to be working on that. It's clustering effects of texts by semantic similarity. And we work with graphs, and we use Crusto, and we use other methods. And I suppose that by doing that, we're hitting one structure.
Right.
Could we have access to this method? And I suppose it's a way of clustering anything, right? If you can represent it in a graph, you can use the structure finding method and cluster your vertices. Yeah, we can access.
Yeah. So to do it, we would use any clustering algorithm as your base algorithm. And once you find the first level, you just simply randomize what you found. And there are different ways of randomizing it, which will affect how well it works. It took us a while to tune it. And then you reapply the algorithm to this modified graph, and you'll get a different set of, you won't find the dominant structure anymore because you randomized it out. So you'll find something else. Okay, now, this work hasn't been published for the following reason. We submitted it to a conference, and they rejected it for the following reason, that we hadn't done enough work in showing that it really found the annotated data. And we couldn't convince them that we didn't want to find the annotated data. If I wanted to know what dorm someone a student at Rice lived in, I looked up in a directory rather than looking all this work. I want to find the hidden stuff that doesn't correspond to anything annotated. But the whole community has been focused on trying to find clusters which agreed with the annotated ground truth, what they call the ground truth. We will try again, and then it'll be out so that someone can actually use our code. But you can write your own. It's not that hard.
Yeah. I mean, we're using a couple of clustering algorithms. The part that I don't understand is the randomizing. I mean, after I discover a set of clusters by using whatever algorithm I make, how do I randomize that structure?
So let me also ask you, how big a graph are you working on?
We're starting with 50,000 tweets, and we also want to use papers with more words. We are vectorizing texts, and we're doing the same explainer, like a number of occurrences in every text, and then we use a formula which is called Sorensen to find the semantic similarity between two texts, and that's our graph. It is weighted, and one method is by comparing every single vertex versus every single one to find and start making clusters. The other one is using Crusto and not using finding the minimum spanning tree and not using the last four something vertices. But for that, we need to know how many clusters we're
community, and you've got the vertices and you've got some edges. So you first ask yourself, what is the density of edges in the graph as a whole? And then you randomly remove edges that are in here to make the density of this the same as outside. But something else you might want to do is also randomly add some and randomly remove more. So you really get rid of the structure. And you have to experiment. But since you're dealing with a reasonably large graph, there's another technique you might want to use. See, if I'm going to, let's say I'm going to partition a graph with 100 million vertices into clusters. If I partition it into 10 clusters, on average, the size of them is going to be 10 million. I don't think that's what you want. I think you probably want maybe a cluster of size 50. So there's another method that we have of finding, if you say, I want all clusters that this person is in of size 50 in a graph of 1 million vertices, there's a way to do that. And that has been published, and if I can send you a copy. And that might be something which would be more useful.
Yeah.
What is your opinion about topological data analysis, these techniques of using persistent homology to study large data sets, developed by Gunnar Carlson and Robert Christ? I don't know if you're familiar with them.
Okay, which was the work again?
Topological data analysis.
Topological data?
Analysis where they use.
I'm not familiar with that piece of work. Somebody else mentioned it to me just the other day, but I'm not familiar, so I'm wondering if, was it done here in Mexico?
No, actually Stanford. It started
It's
with
Stanford.
Gunnar Carlson, and then Robert Christ is also developed.
Yeah, I should look it up because you're the second person.
Well, they use tools from algebraic topology to study large data sets and just try to understand clusters from a topological perspective.
Yeah,
It's different.
yeah, I'm totally unfamiliar with it.
Third one.
Yes.
I've also heard about this, they use homology theory, algebraic topology.
Yeah. It's interesting to me. I better look.
Okay, if there are no further questions, let's thank Jonathan.